All right, we having fun yet? You are?
Yeah. Are you?
I am. I mean, look, it's 2:13 time, right? And today is just a great lecture. You know what today's lecture is about?
Dynamic memory allocation, advanced concepts.
Dynamic memory allocation, advanced concepts, in fact. Or, more specifically, how to write malloc lab. Yes?
Just a general question. When is malloc usually on the website? It says Thursday, April 14th. April 14th is actually a Tuesday.
So I believe malloc is due the 9th. To detangle it from Carnival. April 9th. That's I don't have the official schedule in front of me, but I believe if you check the other, like the Autolab site or the schedule, it's due the 9th. There was some discussion as to, originally it was laid out on top of Carnival, but it was never really laid out on top of Carnival. We were just trying to occupy the time on the schedule so we didn't put something else on top of it. But I believe it's actually due the 9th because we don't like Thursday and Friday are Carnival, right? And then like Saturdays move on and so on. And so we want it due decidedly before Carnival week. And so the idea is if we made it due Thursday before Carnival week, then you could still take 2 late days and that's still only Saturday. Because it's just cruel and unusual punishment or unreasonable expectation or simply not going to happen if we ask for Carnival to be due like Thursday, malloc to be Thursday of Carnival. It's just not happening. So I apologize if there was some confusion. I think that originally we may have shown it differently, but it's planned to be a 2-week lab. It's usually a 2-week lab. It's still a 2-week lab. Doesn't overlap Carnival. All right, let's have some fun. All right. So last class we talked about implicit lists, right? Implicit lists use the size of the block as a pointer to the next block. We basically said, look, if we know that one block is yay big, right, we know where the next one needs to start, right? And so we just use the sizes to walk our way through the list. And so when we began the day, we had a header record that had a size and a bit that said allocated or not. And then we just walked our way through and said, is it free? If it is free, is it big enough for us to use? Right? And that sort of worked. And the bit was even free, right? The bit we used to indicate allocate or not didn't cost us anything because of alignment, right? We don't have things that start at odd addresses. And this system worked for us fairly well until we said, you know what? What happens when someone calls free? When they go to, they go and they take a block and they say, okay, this is now available. We ended up with that false fragmentation problem, right? We had a free block and a free block before it or a free block after it, but it looked like we had 3 smaller blocks, not 1 bigger block. So we said, cool. We can look to the right and ask the question, is it free? And if so, coalesce. Simply change the size here so it's bigger, so it steps to the next block. Great. But we had no way of going left. Right? So we said, okay, no problem. Instead of just having a header, we're going to have a header and a footer. So now what happens is we back up by the size, we start out at the pointer the user has, and back up by the size of the header, we get the header. Right? If we back up some more, we get the predecessor's footer. And that tells us how big the predecessor is so we can skip past it. Right? It's great. But the problem is the list is still ordered in exactly one way. It's still ordered from lowest address to highest address, right? Because that's how we're walking through it. And the other problem is we have no choice but to walk through all of memory. We can't, for example, search only free blocks. So we're taking a lot of extra steps. Used. Okay, finally a free one. Right? We're walking through a whole bunch of memory that's already allocated just to find the memory that's freed. And so explicit lists are going to fix this problem for us. Okay? Oops. Now the idea is just like freshman year, we just have pointers. All right? We still have our header, we still have our footer. But now what we do is we add this idea of previous and next. Now we can organize the list however we want. We still have the implicit list. We still have the size. We can still walk through all of memory by address. No problem. We still have the header and the footer, so we still can find our predecessor and our successor. And now inside the header we also have a previous and next. These can be used to put the list in whatever order we like. They're just pointers, just like freshman year. Make sense? Okay. Now why is it that we only have the previous and next in the header and not as part of the footer? Yeah.
The footer is only there for coalescing.
The footer is only there for coalescing, right? Now what if I happen to want to find, if I happen to want to find the predecessor of the block that is to my left? Yeah.
Then you take the size back to the front and then go one more.
Yeah, like if I happen to want to do that, I don't know why I would, but I still can, right? I just use the size to get to the predecessor, and then I'm at its header, and then can use the next and previous. Okay, so this is great, because now I can organize the list however I want. That means, for example, I can do things like leave out the allocated nodes. Right? My explicit list doesn't have to point to every node in the list. It can point to just the nodes that are free and not the nodes that are allocated. Right there, that's going to speed up my searches, right? Because when I need memory, I'm only searching free memory, not allocated memory. Secondly, I now can start to make real policy decisions. I can say, well, look, do I want to keep this list sorted from smallest to largest, which enables a best fit algorithm? Okay? Or do I want to keep it sorted by size, or what do I want to do with it, right? Now I'm in control. You could, for example, that worst fit algorithm we talked about, right? Sort it from biggest to smallest. Don't recommend that one. Okay. So if I look at an explicit list, I see that I can still use the implicit list to walk through all of memory. I see, however, I also have these forward green and backward, right, previous red pointers. So now I can walk through the list in a different order. Okay. So if I look here, this, and follow this next pointer here, I can then, let's see, I can then follow this next pointer here, and then next pointer here, right? If I look at the previous pointers, I can chase backwards, right? From here to here to here. Boom. End of the example. Okay. So look, when I call malloc, I need to break one of these blocks out. Right? What do I have to do? Well, I have a block. I'm going to decide I'm going to give that whole block to this request, or I'm going to give only part of this block to the request. Why would I give only part of the block to the request? Yeah?
If the block is much larger than the requested memory?
Yeah, if the block is much larger than the requested memory, right? There's enough there to be worth saving. What if the block is a little longer than the request?
Just give it to it.
Just give it to it. It's not worth having a sliver in the list, right? That just takes energy to walk through. Okay. So what am I going to do? Nothing different than freshman year. This is just a linked list. I am going to remove a node from a linked list. Right? Fundamentally, that's all it is. Take the next pointer and skip past it. Take the previous pointer and skip past it. My next previous is now my previous. My previous next is now my next. I've now consumed the whole thing. If I want to put part of it in, no problem. I just go through, write my new header with my new size, and then insert it into the list wherever I want. I remove the old one and reinsert the fragment. Does that make sense? 2 steps. Take the big one out, put the small one in. If you're sorting by size, right, it actually makes sense completely to do that as 2 separate steps, because you may put it into a different position. It's an insertion sort, just like freshman year. Okay? If you're keeping it sorted by address, then it's not really going to go anywhere. So now that we have this freedom, we have all sorts of policies, right? One policy is last in, first out. Every time the user calls free, basically take the block they freed and put it at the head of the list. Treat it like a stack. In theory, this policy is useful because things tend to get reused. If you ask for a block of a particular size, right, and then you free it, you're likely to ask for a block of that size again. The person who's got a loop, and at the top of the loop allocates some structure, and the bottom of the loop frees the structure, and then goes through the loop 30 times. Well, then it's going to be great, because they're going to free it and put it at the head of the list, and malloc it and take it off the head. Free it and put it at the head, malloc it and take it off the head. Right? That's the idea behind a last in, first out, or stack ordered allocator. The problem with this is just that in practice it doesn't work very well. Because in practice what happens is, even if there's a likelihood of using something of exactly the same size very soon, unless it's immediately, it doesn't work. You'll end up having some other request that cuts that into a block or does something else with it or whatever, and then it just doesn't work very well. So it doesn't work as well as one might think it would. You know, the temporal locality doesn't work as well as one might expect, but that's the idea. An address order policy. Basically, when we free something, we look at what the address is, and we put it at that place of the list. The problem with this, right, is that you have to do a search to do that. Right? You have to walk through a list. What's good about this, right? It makes it really easy it makes it really easy to coalesce. But remember, if I want to coalesce, do I actually need my explicit pointers? No, right? I don't. So I don't actually need this to coalesce. I can actually use my implicit pointers before I start and say, okay, I'm freeing this. Look to the left, look to the right. Good. Now I've coalesced. Now I can do something with it. So the policy is of limited value, right, because the implicit list is necessarily address ordered. So if your implicit list is necessarily address ordered, using the explicit pointers to address order just isn't particularly helpful. Does that make sense? You already have that benefit. Okay, so here's a block. The user calls free. What do we do? Okay, well, root node points to it. It points to the successor. The successor's predecessor points backward. Okay. What about in this case? Well, here you can see the list, block, block, block. My next pointers, my previous pointers. Okay. The user calls free. Okay. Splice out the predecessor block. Coalesce both memory blocks. And insert the new block after, at the root of the list. This is a LIFO policy, meaning frees always go at the head. It's stacked. Okay. So I coalesce, and then I put it at the head. This is a weird policy if you really think about it. What's weird about coalescing and using a LIFO policy? Yeah?
A block can get pushed to the top of the list from the bottom if you just free like a tiny bit after it.
Right. So the block can get, a block that I freed, right, a large block, right, might end up getting pushed to the front even if what I freed was a small block. So it's sort of, the cache policy that says I've used it recently, I'm going to use it again soon, so it doesn't work if I coalesce first. Now I end up with a big block at the beginning, right? I'm still going to fragment it again. Okay. Another, sort of another case we have, right? So here we see the block. Here we see a piece of it. Here we see the free, right? There's a free block to its right. There's not a free block to its left. So we're doing a right coalesce. Split out the successor block, coalesce both of these, and insert the new block at the root. So these slides all cover all of these random cases, right? I think this is a case of too many slides. Okay? The process here is really simple. If I want to free something, I first look at the implicit list. I ask, can I coalesce left? If so, I remove the left block, coalesce, and then ask, can I coalesce right? If so, remove the right block and coalesce. Now I have a new block. It's not part of the list, right? Insert it according to whatever my policy is. If my policy is to insert it in address order, great. If my policy is to sort it by size, Great. If my policy is always to put it at the front, great. Does that make sense? Mark my newly free block as freed. If I can coalesce left, remove the block to the left and merge, coalesce. If I can coalesce right, remove the block to the right and coalesce. Now I have the block that I actually need to insert according to my policy. Do that. Yeah.
When you're saying left and right, you mean left and right address-wise, not LIFO-wise. Like if it was in a stack like that, you're not going left and or up and down a stack. You're going left and right in its address in memory.
Correct. When I say left, I mean its exact predecessor to the left.
Okay.
Contiguous to the left.
Okay.
And when I say right, I mean contiguous to the right. Actual addresses. Does that make sense?
Yes, it does. Then.
Okay. So we can carve this out in a million ways, but this is really a rehash of freshman year, and we're past this level of abstraction now, right? We know how to put a node into a linked list and take a node out of a linked list. That's not shocking. Mark it as freed. Look left. Can I coalesce? If so, remove the one to the left and coalesce. Look to the right. Is it free? If so, remove the one to the right, coalesce. Now I have my actual free block, as big as I can make it, inserted according to my policy. Okay. So comparison between explicit lists and implicit lists. Allocate is the linear time, the number of free blocks instead of all blocks. Why is that? Well, allocate is when I call malloc. That's when I'm searching for a block that I can use. Now, in the worst case, I have to walk through all the blocks that are free in memory, not all the blocks in memory. I don't have to walk through the ones that are not free. Okay? So this is much faster as memory starts to become full, right? At the beginning, all of memory is free, no problem. Very rarely am I actually walking through a use block. But as I start to use memory, now more and more of my implicit list, right, contains things that are used, not free. So my searches get longer. The explicit list solves that problem. It's slightly more complicated because you've got pointers in addition to sizes. There's slightly lower utilization, right, and perhaps because my header just got bigger. In addition to the size, it has the previous and next. But remember, it's only the header, not the header and the footer. Okay. The explicit allocator is nice, but most commonly, the explicit allocator is actually part of what's called a segregated list system. And that's what we're going to talk about next. Okay. This is the idea that we have several size classes. Okay. Small, medium, large, large. Okay. What are the size classes? Well, that depends. That's part of your design. That's a design parameter, right? How many size classes you have and what they are design space for your allocator. But the idea here is that I have some relatively small number of design classes, size classes. And when someone calls malloc, if they need something that's very large, right, I use the list of very large things. So I don't have to search through the small stuff. If someone is looking for something small, I start out looking in the small list. And if I have something there, I'm good. If not, I then walk forward to bigger and bigger lists until I can satisfy that request. Does that make sense? So the idea there is if I'm looking for something big, I can skip past and never have to look at small things. If I'm looking for something small, I can start in the smallest size class that would work. And if it's empty, just walk forward to the next biggest class.
So in addition to having a list of blocks, you have a list of lists?
You have a list of lists, yes. So you probably have an array of your explicit lists.
So you would only need to know the class for each array, which could be stored in the list itself, and then not even have to search through all the blocks, just search through the list and compare it as you go along. The list of the block, the list of lists.
Yeah, that's right. You're probably going to have relatively few size classes and use something like an if statement or a set of if statements, something like that, just to pick the right size class. And like I said, the trick comes, right, if the size class you're looking for is empty, you need to walk forward to the next largest size class. Because maybe I'm looking for something that's 4 bytes, that's 4 bytes large. I don't have anything in my 4-byte class, but I can still use something that's 8 bytes large. I take my 8-byte thing, I allocate a 4-byte chunk of it, and I put the other 4 bytes into my 4-byte class. 4 bytes is really small. This makes a lot more sense if we view these as like in terms of k, like 1 to 2k, 3k, 4k, 5 to 8k, 9k or more, something like that. This is completely arbitrary, really. Okay? And the idea there is just to search things that are more relevant. Why walk through the small stuff if I need the large stuff? Without being so rigid that if I don't have anything of the right size, I get stuck. Just keep walking. What do you do if you look in the largest size class and it's empty? What's that? Yeah, but so what do I do then? Well, let's say I'm let's say I'm coalescing as I go, doing constant time coalesce. What's that? Okay, so my caching allocator, my malloc allocator doesn't have a block that's big enough. So what does it do? Allocates more memory from where? It could be, but yeah.
Why can't you just go to the next smallest block and combine them?
Well, because we've already coalesced anything that's actually contiguous. So I can't take a block from over here and a block from over here and use them as one array. Yeah.
You could find the biggest block, and if like stuff next to it is smaller or bigger, you can move that around.
Where does malloc get its memory from?
System.
I heard it whispered.
The heap.
The heap.
Expand the heap.
Grow the heap. How do we grow the heap?
S-break.
S-break or break, right? We move the breakpoint up. So if we end up looking, starting here, nothing of size 4, nothing of size 5 through 8, nothing in here at all, okay, that's the point we call S-break. We raise S-break, we call S-break, we raise the breakpoint. We get a whole bunch more big blocks. They basically land here in the biggest size class, and then we can tear them down. Does that make sense?
What happens if we can't do that?
If you call break and break fails, so if you call break and it turns out that it's on top of your stack, or if you call break and it turns out it's on top of some read-only library serving as a guard page, you cry. Because now your stack is huge and you've got a problem. That's the point where you're dealing with a fairly specialized program, and you've got to do things like link your shared libraries yourself to get them high, right, out of the way. To avoid those guard pages. And you've got to make sure that your stack is going to stay very small then, right? And eventually, you'll just run out of address space. But, that exasperated, sigh over here, that's about right? That's not going to really happen, I hope. 64-bit machines have a lot of address space. So you have an array of free lists, each one for some size class. To allocate a block of size n, you search the appropriate free list. If you find it, you celebrate. You take that block, right? You mark it, you take that block, you look at it and say, okay, I have a block yay big, I need a block this big. What do I do with this? A, give it to the user and forget about it. Great. Mark the block as allocated, take it out of the doubly linked list. Or B, no, that leftover piece is useful. It's big enough to go into one of my size classes. So now you remove the block from the list, right? You reset the size, right? And then you take the small one and you insert it into the appropriate size class. Does that make sense? If no block is found, you use S-break, beg for more memory. To free a block, well, the first thing you want to do is see if you can coalesce. Use the implicit list to look left and look right. Look left, is it free? If it is free, remove it and coalesce it. Look right, is it free? If it is free, remove it and coalesce it. Yes?
Sorry, what are you going to do the difference between S-break and realloc? And doesn't realloc also ask for more memory?
Okay, what's the difference between S-break and realloc? S-break is the, do you want to go ahead and answer? Sure.
Realloc is the thing that the user needs to use. S-break is the thing that the person allocating the memory needs to use.
Yeah, realloc, like malloc, is a user-level API call, right? S-break is something that malloc will use. So S-break raises the breakpoint. That's all it does. It says the heap now goes to here. 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 It keeps moving the heap up. But that's all it does. Now that memory properly belongs to your program, you need to like carve it up among your program's many needs. And that's what the malloc allocator does for you. So, malloc or realloc, right, go to this set of segregated lists and find memory that they acquired via sbreak or sbreak. Okay? So what happens is if you call realloc, realloc uses the implicit list to look to the right. Do I have a free block exactly to the right? If so, is it big enough? Right? Will that get me to the right size? If the answer is yes, then it's going to merge those two blocks. It's going to change the size on the original block to the left, both in its header and footer. Right? It's going to change the pointers so there's only one block in that list. If the sliver left over is worth it, it'll insert it somewhere else. Give it a header, give it a footer, put it in. Okay? sbreak simply says the new breakpoint is here. Does that answer your question? Okay, excellent. Okay, so the advantages of a segregated allocator. The advantage of a segregated allocator is that you get higher throughput. Why do you get higher throughput? You're not searching through small things if you're looking for something big. Okay? Sometimes you use what's called a power of 2 allocator. That is to say your size class is a power of 2. If you do that, right, you end up with a search time that's logarithmic. Why? If my size class is powers of 2, why is the search time for the right size class logarithmic? Yeah. Because it's what? So it's certainly sorted, right? So you can do a binary search. Does that make sense? Basically, if my size are power of 2, and I know that it's, you can imagine that if I'm looking for something, right? In the worst case, I'm taking a block of size x and dividing it into a block of size x divided by 2, x divided by 4, x divided by 8, and so on. Right? Okay. Better memory utilization. That's an interesting one. Why better memory utilization? Well, as it turns out, right, the two policies that make the most sense in terms of dealing with allocation, right, are first fit and best fit. We said that the LIFO policy, although an interesting idea, doesn't actually work out because a simple stack isn't good enough to exploit locality. Too much can disrupt it. And we said that the worst fit policy, which in theory put the biggest thing back into the list, actually turned out to be a mess because it just guaranteed the most fragmentation. Okay? So the two policies that made the most sense were first fit and best fit. Why best fit? Because it minimized fragmentation. But what was its cost? That we had to sort by address. Why first fit? It was fast. We didn't have to sort anything. Okay? So the thing about a segregated list is it lets us be fast, like first fit, right? Sorry, yeah, it lets us be fast, it lets us be fast without the need to sort, sort of like first fit, right? But gives us size classes that make sure we're not doing something silly, right? Sort of like best fit. We're in a size class that's reasonable, right? Having had to make very few decisions. Okay? So if you think about it, if I have a few size classes, right? Within a few if statements, I can land at a size class that's reasonable. And now anything I find is pretty good. Does that make sense? At the extreme, I have one size class for every possible size. 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes, 6 bytes, 7 bytes, 8 bytes, 9 bytes. You get the idea. Okay? If I would do that, that would be basically the same as best fit. I'd end up making so many decisions to find the right size class that I might as well have sorted it. Okay? Yes?
That was just what I was going to ask, that aren't we basically sorting it by putting it in a different class?
Yeah, you're basically sorting it by putting it into different classes. But the idea here is that it's a very broad sort, right? So if I have just a dozen classes, I'm only making a dozen decisions. Buckets, right? And the good thing about that is it's very fast to make that dozen set of decisions, and it also rules out a lot of ridiculous possibilities. Does that make sense? My bucket's all a pretty good match at this point. And so it really turns out to be a nice balance. The speed of a first fit with a lot of the efficiency of a best fit. And think of it this way. A perfect best fit may not be any better at all than something slightly worse than a best fit, because if we have 1 byte left over, or 2 bytes left over, or 3 bytes left over, it doesn't matter. We may just give them to the user anyway, right? It'd be a rare case where we actually get to use that byte. Right? If I have something that's size, 3,000 bytes, and I give the user something that's 3,004 bytes. For that to matter, I'd have to have something that's 3,001, 3,002, 3,003 bytes. Right? 3,004 bytes. Unlikely. The art of computer programming, is a sort of of course a seminal work. It really has a detailed study of allocators. Before the art of computer programming, there was a lot of debate about what these policies should be. Like I said, worst fit was discussed as a viable alternative to reduced fragmentation, and Knuth sort of put all of that to bed. He did a fairly, he established a fairly interesting model and did a fairly formal proof of it, and also did a huge amount of empirical study. And so if you read that, it's sort of settled as to what the trade-offs are. Very, very thorough, beautiful discussion. Sometimes Knuth is a little much for people, but if you actually care about memory allocators and their efficiencies, it's a great thing to read. Dynamic storage allocation survey and critical review. It's sort of a comprehensive survey. It's a good paper. Okay. So memory allocators. So what we've talked about so far, right, are the situations where the programmer is explicitly in control of malloc and free. Give me, take back. Right? But many programming languages don't work that way. Right? Think about other languages. Python, Java, Ruby. Right? These things don't work that way. Programmers say, give me, right? We create objects. And every time we instantiate a new object, right, there is an allocation that's required to do that. So we're sort of explicitly asking for memory. But we never actually, explicitly free it, right? Java has no free. Python has no free, right? So it's garbage collected. So the idea here is somehow, right? Somehow the runtime environment, and note that I said runtime environment, right? It's not the compiler. The compiler happens before the program ever runs. Memory usage is dynamic. It depends on what the program does. If the user enters more data, you may need a bigger buffer, right? That's the reason we have dynamic allocation. So the runtime environment somehow keeps track of what's used and what's not. It is able to free memory that's not used or usable. Okay. So what to say? Here's an explicit request for memory. Oh, I think my battery's died. My laser died, but you guys can't see that anymore. Okay. So malloc is an explicit request for memory. Right? This is asking for 128 bytes. Right? If we don't have a free, the question is, how does that free? How does the memory manager know when memory can be freed? At some level, we can't know what the future will bring. The memory manager can't say, well, I'm going to look in my crystal ball, and if you're never going to use this again, I'm going to free it. Right? A memory manager can't say, I'm going to free this after the last time you use it, because it has no way to know what your program is going to do in the future. If it is usable, it might be used. Does that make sense? So we're really going to be concerned about things that are not usable. certain blocks that cannot be used because there are no pointers or references to them. If I have an object and nothing points to it, is there any way to identify it? Not by the program, right? If the program can't even talk about it, can it use it? No, right? If I have a pointer to a string in C, and I set my pointer to null, can I use that string? No, not unless there's another pointer to it, right? If I have an object in Java and set the only reference to it to null, can I reference that object? No, it's useless. It's floating in space. Okay? So basically, if the runtime environment can identify objects that are floating in space, it can free them for us. Does that make sense? Now, as you might imagine, that's an expensive process. It's much easier to identify the things that have names than the things that don't. Right? Right now, it'd be much easier for me to tell people who are in class than people who are missing. Right? Finding out who's missing is a harder problem. That's the problem garbage collection tries to solve, right? Who can't be referenced? Now, to do this, we have to be able to make certain assumptions. Memory managers have to be able to distinguish pointers from non-pointers. Okay? If I can take a pointer, cast it as an integer, add 4 bytes, and cast it back, and that's a valid pointer, there's no way that's going to get figured out, right? It has to know when there's a number in the system, if that number represents the address of an object or the name of an object in some capacity, or is just some random number. Okay? We need to have strongly typed pointers, or references. All pointers have to be names for the object. Okay? It can't be the situation that, okay, I have a pointer to some object. I have a reference to some object. And now I can suddenly point at the middle of it. That's not going to work, right? Because we can't view pointers if we have them as addresses. We have to view them as names, identifiers. Okay? So this thing is saying pointer, and it's really important that from the perspective of a garbage collector, you know, I could say pointer, I could say reference. It's the name of the object. It's an entity that it can keep track of. Okay? So what all of this boils down to here under must make assumptions about pointers, right, is basically this. We have to be able to identify objects. And the system has to know what is an object and what is not an object, right? The system has to know about the total set of objects and has to know which of those total set of objects are being used. Then it can identify the objects that are not being used. If we can create new objects by moving a pointer whenever we want, it has no idea. Okay? You can't hide pointers, such as my example about casting to an int and back. There are all sorts of classic algorithms. You can see that the 60s was a big time for studying this. Mark and sweep, reference counting, copy collection. The 80s, generational collectors. Garbage collection algorithms for automatic dynamic memory, 1996. Good book. Okay. The idea here is that we want to view memory as a graph. Okay? We want to think about these objects, and we want to think about how they relate to each other. This object identifies this object, identifies that object, and that object, and that object, right? We want to think about how these pointers or references connect these objects. Because at the end of the day, if I can't reference an object directly or indirectly, it can't be used. Think about a linked list. Okay? There's a pointer to the head of the list, right? That's how I identify the head of the list. Once I get to the head of the list, I can find the next node, and the next node, and the next node, the next node, the next node, the next node, and the next node all the way to the tail, right? So as long as I have the head pointer, everything else is fine. But suddenly, if I remove that head pointer, I've made the whole rest of that list an island. Right? The last node of that list still has a predecessor pointing to it. Yet it can't be accessed. Why? Well, that predecessor, although it has a pointer pointing to it, can't be accessed. Why its predecessor, although it has a pointer pointing to it, can't be accessed? Why? Because what used to be the head of the list can't be accessed. We can't get to the list to get to the successors. Does that make sense? Remove the pointer to the top of a binary search tree, and the whole tree now becomes an island. So the bottom line is this. We have to have some set of root or distinguished nodes. Things that we can find. Once we have those, what we're going to basically have to be able to do is see where can we get from there. Start out with certain node points and basically figure out everywhere we can go from there. Okay? Imagine that we start out with our known points, our 3 green root nodes, and then we color our graph. Just imagine flood filling it. Anything that we colored is safe. It's reachable. But anything that we couldn't color is unreachable and can be freed. Does that make sense? So that's what mark and sweep does. It goes through and marks everything it can reach, and then sweeps and gets rid of everything it couldn't. Does that make sense? So the first thing it does is, starting out with these distinguished root nodes, finds everything findable. The second thing it does is starts out with some list of every object in the system and walks through and looks at every object, and if it wasn't marked, throws it away. Frees it. Does that make sense? This is not a fast process. And it's a very complicated process, as you can imagine, if you're still able to change the graph. Yeah. Oh shit. Right? Basically, you want to freeze memory allocation when you do this. So it's very disruptive. So when do you think is the best time to do this? What's that? Well, at the end of the program in some sense, but at the end of the program I don't need to do it, because when a program ends, all of its memory gets freed. And we'll learn how that works. We haven't learned that yet. We'll learn how that works when we look at virtual memory. What's that? Okay, maybe at the end of a function call, but yeah.
User input's going on?
Maybe when something else is going on, yeah. When you need memory, right? Maybe the best policy is don't bother with any of this because it's slow and disruptive and it'll interfere with your program unless and until we need to. Then go through and pay the piper and sweep. Does that make sense? So at least one reasonable policy is not to mark and sweep unless and until you need to, because many programs are short-lived. Having said that, not every program is short-lived. And some programs have a huge number of objects, right? And thrash through objects very quickly. And so if that's the case, if your program has a long lifetime and rapidly consumes, allocates and frees objects, you may actually have to adopt another strategy, such as try to do this when I/O is happening, or something like that, when the program is otherwise blocked. Pick a convenient time. Yes?
So we were saying when you run out of space, are you referring to when you can't S-break or when you S-break?
I am referring to when you can't S-break. And the reason for this is basically what happens is, right, I don't care much about RAM at this point, because what happens is old objects that haven't been used for a while get swapped to disk. And that's virtually free. And the reason it's virtually free is these days, when the disk is doing nothing else, we just write out dirty pages. That way, we can just use them when we want. Does that make sense? And so if we do that, the cost to us is nothing until we actually have to free them. And then that requires some work. Just accounting at that point, right? Because when I free it, it's not like I need to swap it in to free it. I just need to do the accounting. So you're right. Basically, our strategy is, depending upon how our program works, try to avoid doing this. If we can never do garbage collection, that's the best policy. Okay? If that won't work for us because our program has a long life and is eventually going to generate junk, as you suggested, pick a good time. Okay. So we can actually build a mark and sweep allocator on top of malloc and free. But to do this, we're going to need to have some constraints. Here's how it's going to work. We're going to use an extra bit, a mark bit, in the head of each block. So the head of each block right now has the allocator unallocated bit. we're going to give ourselves a bit to let us paint it when we do the mark phase. Okay? We're going to have mark, which starts out at a root node and travels around and marks everything, right, that it can reach. And then we have a sweep phase that's going to walk through every allocation and basically call free on anything that's unreachable. Does that make sense? So we put the mark bit, the bit that we need for the mark phase, into the header, just like the allocate bit. And again, that is free to us because we, basically alignment means we're not going to have things that have 2's in the addresses anyway. Okay. So I start out with a root node, and then from there I can chase the rest. And you can see that as I go through, I set my mark bit to everything that's reachable. And then when I do my sweep phase, if it's not reachable, I free it. Okay. And notice that the strategy here says allocate using malloc until you run out of space. Once you run out of space, there's no cost to this because you couldn't do anything anyway. So if your program delays while you mark and sweep, that delay is better than dying. Right? It's better than malloc returning null. Now, I said that to do this, we'd have to operate in certain constraints, right? We can't go about business as usual with malloc because, as it turns out right now, right, we really have no idea what the set of all objects in the system are, right? There's really no general concept in a C programmer's mind about a root node, right? So we need to simplify things here, add some constraints until we understand that we have a way of understanding what every object in the system is and where we're going to start this little traversal, okay? So here's our API. New is going to return a pointer to a new block. Okay. So this is sort of a replacement for malloc, right? And it's going to give us the address of a new block. We have these macros read and write. Okay. So read is going to read byte I of block B. Write is going to write value V into block I of block B. Right? Each block is going to have a header. We get to the header by backing up, right? Just like we did before. We have to have a function that tells us if something's a pointer, right? Does it identify an object? I have to be able to tell a pointer from an integer, from a float, from a char, from everything else. And I need to be able to figure out the length of a block. If I can't figure out the length of a block, I can't figure out where the other blocks are. I need a function that can find my roots. Unless I find my distinguished nodes, my root nodes, I can't go through my mark phase. Okay. So what does mark do? Mark asks the question, is this a pointer? Okay. If it's not a pointer, it's just some data value. We're done. There's nothing to mark. I can only mark objects, right? How does it know it's a pointer? We're going to know that because we call new, we'll be able to identify pointers, right? New creates pointers. So now we can figure out what the pointers are. So is pointer can tell us whether or not something's a pointer. If it's anything other than something returned by new, it's not a pointer. Okay, for this purpose. It's not a pointer into the heap. Okay? We ask if the mark bit is set. If the mark bit is already set, that means that we've got to the same location via our graph already. Just like graph traversals, sophomore year, right? For many of you, I guess now, you don't want to go around and 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 around, right? You want to know if you've been there and stop. And so if it is in fact a pointer, and in fact we haven't been there, then we set the mark bit. Now we find out how big that block is. And for each byte of that block, we ask the question, is it a pointer? And now it's just, now it's recursive. You see that? For each byte of the block, we call mark. And now we repeat, is it a pointer? If it's not a pointer, we're done. We're going to return back here, check the next item. Is it a pointer? If not, we're done. Return here, next step in the loop. Is it a pointer? Sure it is. Is it marked? Yes, it is. Okay, we're done. Return here, check the next one. Okay, is it a pointer? Yes, it is. Is it marked? No, it's not. Okay, now we're actually going to go through this again. We're going to set the mark bit and dive in. It's just a flood fill. Okay. Sweep is really easy. Okay. We walk through all of memory, and if the mark bit is set, we clear the mark bit. If the mark bit isn't set, we were not able to reach it, so we free it. Okay. Now we step to the next block. Okay. So is pointer obviously determines if a word is a pointer by checking if it points to an allocated block of memory. We allocate blocks of memory by new, so we know what we've allocated. How do we find the beginning of a block? An easy way of doing this is to use some type of search tree. Right, to avoid the bad behaviors of degenerate trees, some type of balanced search tree. Okay, an AVL tree, right? A splay tree, red-black tree, something like that. Okay, and now we search. And so somehow we do a tree search for an address and see, is this address in our tree? If it is, it was allocated. If it's not, it wasn't. Does that make sense? And again, this tree is being built by new. That's the only way we can allocate a block is by new. So every time we call new, we insert something into the tree. Every time we want to know if something's a pointer, we look for that address in our tree. You guys have programmed C long enough to know that when you're given sort of a relatively unconstrained memory system like C has, a memory system where the way we identify objects is by their address, and where we can actively change that address as if it was a pointer, we can make all sorts of mistakes. Right? You've been playing this game long enough to know that in a system where we don't have runtime bounds checking, we can make all sorts of mistakes and not know for a while, right? So there's all sorts of stuff, in this world, in this, world of C memory allocation that can be painful. Let's walk through that list. We can dereference bad pointers. Okay. What's a bad pointer? Well, that's something that's already been freed. That's something that has been mucked with and now doesn't point at a valid block. Maybe we did pointer arithmetic badly. Okay. Maybe we had an uninitialized pointer variable. We can read uninitialized memory. Right? The classic example there is assuming incorrectly that malloc zeroes memory. Right? You want calloc for that. You can overwrite memory. Right? Two different linked lists point to the same object. They've aliased it. And now using one list, we change the object. And now it changes the object from the perspective of the other thing. We have an array, and we overwrite past the end of the array onto some other object, sometimes off by one error. We can reference non-existent variables. That is, we can freeze something and then try to use it. Okay? We can freeze something multiple times. We can let cruft build up, never free it. Why is that a problem? Why is it a problem to never free anything? What's that? Memory leaks. So what?
You're going to have a hard time finding memory that's free.
I have a hard time finding memory that's free. Have I told you my malloc story? My grad school project? So my master's project involved writing a proxy server that allowed you to access some stuff on a DoD network from the everyday internet. And it basically parsed all the traffic to make sure that the traffic was legal. And I was like, a bad grad student. I mean, I did all of my work the night before my advisor meeting. It wasn't a good strategy, but, it worked for me sometimes, mostly, occasionally. And so there was one night that I was working on this, and, I was in one of those modes where I could actually just hack at a high speed, but I couldn't actually think. If I knew exactly what I wanted to write, I could code away really quickly. My brain was to the point where I was settled into my chair and hacking away. But I just couldn't think. It actually involved figuring out what to do. Like, I was too sleepless for that. And so I got to a point where I had to figure out the maximum size a buffer could be. And I just was afraid I was going to get the math wrong. And so I just quickly wrote this thing that called malloc on a very large number, and if it wasn't good enough, called malloc again. And I only intended this to get me through my advisor meeting the next day. I didn't actually intend to leave it there. And so I never bothered to free it, because I intended to come back the next day after my advisor meeting and figure out how big this thing really should be and make it a static buffer. But I was up really late, and I was really sleepless. And when you get really late, it gets really late, and you get really sleepless, your memory doesn't work really well. And so I shouldn't say never again, but not for a very long time did that particular memory allocation come to mind. And initially, this proxy server was put into production, and everybody loved it. Then the DoD had the realization that actually they could use this for all sorts of other types of data too. And they put large databases behind it. So they had a large database, my proxy server, and an application that used a large database. And now the average page size flying through this went from, a few dozen bytes to a few dozen kilobytes to megabytes and megabytes. And so as this happened, they started using it for more and more and bigger things. We started getting complaints that it was slow. And I initially didn't take the complaints really seriously, because they sounded to me of the form, when we do more work, it takes longer. And I'm thinking, okay, well, that doesn't sound unreasonable to me. And then one day, my bosses, a couple of faculty members summoned me and said, we really need to address this problem. I'm like, okay, cool. I'm a systems person. I like optimization. I'll go optimize away. And so I went through and I did a code level optimization, where I did things like looked at the order of tests in a while loop and optimized them for those that were most likely to short circuit first. And compacted some things, did some other code level tricks, and I think I got like a 2% optimization or something out of that. I was happy. They were less than happy. So I went back to work and used a caching strategy to build a compressor that that basically kept track of different substrings in the data it was seeing, and built a dictionary and had a cache. And I think that got a 7% performance improvement, because now I was able to send single indexes. It was sort of Huffman tree-like, but a text version, right? I think that got a 7% performance improvement. So I was really happy. 3 times the improvement I had last time. They were still not happy. So we had this meeting with my 2 advisors, and one of them was a systems person. The other one was a languages and compilers person. More of a PL person, though. And so the person who was the systems person gave me the advice and said, well, human intuition is often a poor indicator of system performance. And the compilers person, or I should say more programming languages person more than the compilers person, more of a PL theory person, said to me, well, it's almost like, after a certain point, the wires take a long time to warm up. And he said, let me rephrase that. It seems like the amount of time it takes gets longer and longer and longer with more data. As the data size is going up, right, the delay is going up faster. So I left this meeting, and I'm thinking, okay, so one advisor is telling me that, that the more work I do, the longer it takes. I don't really know what the other guy's telling me. And so I went back and mucked around doing some more optimization. I don't even remember what I got out of it, but certainly not what they wanted. So for some unbelievable reason, they actually hired me on the faculty over there. And one day I was sitting in my faculty office, and my old advisor, the systems person, walks in and does one of these. And so I followed him over to his office. And on his, huge screen over there in his office, I saw the code from my proxy server. And I saw on that window, what? The malloc. And I immediately started apologizing for that malloc, not realizing this had to do with the performance problem. I thought he had to get the code, peer reviewed by the, for DoD purposes, and they called him on that being a memory leak or something, right? And then he pointed at the strace, and strace, what it does is traces every system call, and just gives you a list of system calls. Break was called like 40,000 times in this run of this program, which must have taken a second and a half. What happened? Right? This thing was in an innermost work loop, right? Every time it needed a new buffer to read a few more bytes, it basically called malloc again. Didn't free it at the end of the loop, and drove the heap all the way up. Right? Until the point where the system was actually paging because the write-out couldn't keep up with the use of memory. Because in effect, all the memory my thing was trying to use was coming from disk at that point. Because it ran through all of its actual core, and then as it started to have to call break, it had to swap, right? Because this was in the innermost work loop. And so in effect, my program, beyond a certain point, was running at the speed of disk. And then I started profusely apologizing and offering to fix it, and of course he already had. And then I realized what the advice that I got actually meant. Right? When he said that human intuition is a poor indicator of system performance, what he was telling me to do was profile it and see where the thing was actually spending its time. Quit guessing. Like, you're sitting there optimizing random things. Why? Like, the program is doing something for the 10 seconds it's waiting around. Go figure out what. Right? Which is what he did when he ran strace to see like what the program is doing. Right? Because he probably started out running gprof and saw that there were that it spent a huge amount of time in sbreak, and then ran strace and saw that the reason it was spending a huge amount of time in sbreak is because sbreak was called a lot. And he probably could have gotten that output from gprof 2 if he had the right flags, right? And so that's what that advice meant, right? And what was the other advisor trying to tell me? Right? The other advisor was trying to tell me you're exhausting some resource and then it's getting slower. Right? It seems like after a while, right, it's getting really, really slow. Figure out what that a while is. Right? That a while is when you run out of core and start using disk as memory. Right? So that's my malloc story. So failing to free blocks actually can make a huge difference sometimes. Okay. In star p. So in star is the type, p is the variable. P is a pointer to an integer. Okay? In star p bracket 13 bracket. Okay? What's going on there? So p, right, is an array of 13 pointers to integer. It's int star p13. Int star is the type. So p is an array of 13 pointers to an integer. Just like if I had int p bracket 13 bracket. That would be an array of 13 integers. So int star is the type, p bracket 13 bracket. Okay? So we parse that with the int star being the type, and then the rest of that being a description of the array. Int star star p, sometimes called an integer handle, is a pointer to an integer pointer, right? Here, we've moved our parentheses. We've changed our association, right? At some level, this is still int star p13, right? But notice the parentheses now are pulling that star from the integer to the p. So my type is now an integer. So p is a pointer to an array of 13 integers, because I pulled that star from the integer, from the type, over to p. Okay? In star f, well, you know, f is a function returning a pointer to an integer, right? Because this is just the same as if that was float f, right? That would be a function that returned a float. This is in star f. It's a function that returns an integer. Here, again, I've added a set of parentheses here. Okay? So now that pointer is not part of the return type, it's part of the description of f. F is a pointer to a function returning an integer. And then for these last two, I don't care if these make any sense to you at all, quite honestly. Because you should never write code that looks like this. If somebody does write code that looks like this, the reason you're reading it is probably because they screwed it up and there's a bug. So don't figure out what it does. Figure out what it's intended to do. And then fix it. What's your friend when you're trying to make things that read like that sensible?
Delete.
How can we make types like this easier to read? Error whisper. Type def. Yes, start to type def this out, right, until it actually makes some sense. Because this is ridiculous. Like, don't do that. F is a function returning a pointer to an integer array of 13. A pointer is to functions returning an int. Good. X is an array of 3 of pointers to functions returning pointers to an array of 5 ints. Good. Ah! Type def. Oh, who cares? If you care, offline, walk your way through this stuff. If it takes you 10 lines and a step, you know, to write out the type, like type def it. Right? Type defs allow you basically to comment this. Right? Because each of these things that we have a line here as we build this out can be type defed such that we know what it is. Yeah, moving on. Yeah, whatever. A better way. Type def. So a pointer to a function returning integer. So I type def something, pointer function returning integer, PFRI. Okay? Now, from that point, I have PFRI. It is going to be a pointer to something, you know, to a function returning pointer integer. Now I can do another type def, right, where I have an array of 13 of those. Right? Now I can do another type def where I have a pointer to that. Now I can do another type def where I have a pointer to a function returning a pointer to that mess. So now somebody can actually read this and say this is a, you know, and look at this and say this is a pointer to a function, you know, to a function returning an array of 13 functions returning, you know, I have to go trace my way back here, but I can, right, arrays of 13 pointers to functions returning integers. Right? It actually serves to comment every part of that. It doesn't make it any less complex, but at least means that I can trace this backward and know what each part's supposed to mean. Dereferencing bad pointers, we know this game, right? We did this all, everybody did this as the first time they programmed in C, right? The first thing you did is tried to scan into an integer. Oops. Then you were smart and read the man page. And it said that should be an integer pointer. So you added a star before val. How many people did that? Yeah, the rest of you lie. Right? And now you had a pointer into space, right? Maybe it worked for a while, maybe you got a segment fault, right? Pretty classic. Reading from uninitialized memory. Right? So malloc doesn't zero anything. Don't assume it does. Use calloc if you care. A wrong-sized object. You know, n versus m, right? Another classic example is an off by 1 error. Get s, right? Overwriting memory. Allocate a buffer yay big. You guys know the drill from Buff Lab. Use a buffer yay big. Oops. It's overwriting past the end of that buffer onto who knows what. Pointer arithmetic. Remember that if you add something to a pointer type, it adds a multiple of the type. So if you add 5 to an integer pointer, it's adding 5 times the size of an integer, not just simply 5. Referencing a pointer instead of whatever it points to. Okay. Here we have, int star packet. Packet equals bin heap. Bin heap of 0 equals bin heap of star size minus 1. Let's see what we get. Okay, who sees the error?
It's not going to return. It's going to return a garbage value. The pointers.
How many people think you see the error? Take a minute. Okay, just hang on a minute. Take a minute and let everybody figure it out. Let's not rush anybody. How many people think you have it? 1, 2. Anybody else? Anybody in the back? You got it? You got it? You have it? What do you think it is?
It's referencing the pointer to size rather than value.
Where?
When you increment the size, when you increment the third line in the function.
Where it says bin heap of star size?
Yeah.
Okay, so what do we think the problem is there?
It should just be size.
Why? I'm not seeing that bug. Maybe I'm not seeing it. Okay. What do you think? Okay, go ahead. Well, do you have an idea? Yell it out.
Well, for one thing, packet was defined locally.
Okay, so packet's a local variable, but it's pointing to something that's being passed in, right? So bin heap, right? Bin heap is something being passed in. Okay.
So when you return it, you're returning the pointer, you're not returning the object that it's pointing to.
Okay. So if I look at this, right? Packet is assigned equal to bin heap of 0, right? Bin heap of 0, right? Is a pointer. Do we see that? That's probably not actually what we want. We probably want the node. Okay. Referencing non-existent variables. right? What's going on here? Val is on the stack. The stack goes away when the function returns. By the time this returns the value, the address of that value is technically unallocated. If we use it for a while, the next time we make a function call, we'll scribble over it. Freeing blocks multiple times. In general, this is the result of bad conventions, right? You want to have a strong convention as to who creates an object and to who destroys it. Right? If you're calling a library, that library should there should be some convention, right? The library allocates everything and the library frees everything. The caller allocates everything and the caller frees everything. You don't want to have confusion where some objects are allocated by the caller and some are allocated by the library, and some are freed by the caller and some are freed by the library, because then you're going to end up in a situation where the programmer's confused and they're both going to free something. Referencing a freed block. Again, if your convention is bad, the library can free something and you still think it's good. We talked about this. This is my favorite. The malloc and no free. Freeing only part of a data structure. If you have a linked list, and each node of the linked list points to an object, and you go through and free all the nodes of the linked list, but you don't free the nodes they point to. Oops. Of course, there's the corollary, right? Where you have two different linked lists. One sorting users by last name, one sorting users by first name.
And you go and free them both.
And then you say, okay, I'm done with first names, free that. And do a deep free. And now your last name data structure is broken. Oops. Dealing with memory errors. GDB is your friend, right? If you get a seg fault, GDB can show you exactly where it happened. Maybe that's not where the problem is, but that's exactly where you first saw the problem, right? It's great. We have a debugging malloc. Environment variables control the behavior of malloc. And it can help you find all sorts of problems. Okay? My best friend is valgrind. Right? Valgrind actually tells you what's going on at runtime, right? Sort of like a debugging malloc is, but they can find many more types of errors. It actually rewrites sections of the executables, so it can do more. Bad pointers, overwriting things, off by n errors, referencing outside of blocks. Or, of course, you can use a language like Java or Python, not worry about any of this. Ruby. Any questions? Yes?
Does Valgrind do anything that GDB doesn't, or vice versa?
Yeah, Valgrind is much more powerful than GDB.
Does GDB do anything that Valgrind doesn't?
No, Valgrind gets much more information because it actually instruments the code, whereas the debugging malloc just works from the perspective of malloc. Have a great